In this video, I am hopefully going to help you out, save you from some frustration by using this slightly slow render engine. And that is by optimizing things, hopefully reducing your render time by quite a bit and reducing noise. Now there are two kinds of optimizations you can do. Non-destructive optimization and destructive optimization. Now, non-destructive is things like adjusting the render settings to guide the samples to the areas that you want to give more samples to, the noisy areas. And then you have destructive sampling, where you're compromising a bit on the quality of your render, or the accuracy of your render rather, in order to get less noise and reduce the render times. So let's start with the non-destructive stuff, the render settings. So if I just go and render this right now with 20 samples, you can see that it is full of noise, which is great. That gives us something to work with. So the first thing I want to show you is something I've showed you before, and that is the multiple importance sampling of the world setting rather. So if I just go and enable this and render it in a new slot, you can see that it is quite a bit less noisy. So if we zoom all the way in and go back to the first render, this is with multiple importance sampling, or MIS, off, and this is with it on, so it's much cleaner as well. And that's what that basically does, is it tells Blender to sample the brighter areas of our HDRI more than the dark areas. That's pretty cool. But the other thing we can do is increase the map resolution. So let's go to a new slot, set the map resolution to 2048, which is the same as the resolution of my HDR. And you can see that it is even cleaner. That is pretty cool. So this is with it off, this is with it on, with the resolution of 256, and this is a resolution of 2048. And you can see it gets rid of all of those horrible fireflies. And that is cool. The next little thing I want to show you is this pattern over here. Now we've got a choice between Sobble and correlated multi-jitter. Now I know that sounds like a bunch of mumbo jumbo, and it kind of is. It's just a different algorithm for calculating where the samples should go. So if we change this to correlated multi-jitter, go to a new slot and render that, it looks pretty much the same. I mean, it is, let's see, a little bit over a second slower, but if we zoom all the way in to, say, our diffuse shader over here, it does look a little bit cleaner. This is the correlated multi-jitter, and this is the Sobble. Now, it's very similar. I mean, it doesn't make too much difference, but depending on your scene, it might help you. It might make it too slow for you, but hopefully it'll do a little bit of a better job. Basically, all of these optimization tips that I'll give you now depend on your scene completely. Anything you do might make it worse, it might make it better, it might do nothing at all. It's really up to you to try it out. So after that is Progressive Refine. Now this guy over here is recommended quite often. It surprises me how many times people say that you should use this, and they are completely wrong. And let me just show you by example. So this is our render, which takes 12 seconds. Let's go to a new slot, turn this on, and render it. Now the reason people recommend this is because maybe you don't know how many samples you want to do. Maybe you want to render an infinite number of samples and stop it in a few days' time when you feel like it, which is cool. But it is a lot slower. Now, as you can see, our previous render was 12 seconds, and now all of a sudden it is 16 seconds. Now, that's not very much, that's 4 seconds, but if you have a render that takes 4 hours, it might take 6 or 8 hours instead. So that's kind of a compromise, and this is using CPU rendering. In some scenes I've noticed when using GPU rendering, it can take even 3 times longer when you enable this. And the reason this is slow is because it's constantly changing tiles. Every time it renders one sample, it's got to change to a new tile and look at the geometry and decide what to render and where the sample should go. Whereas when it's off, it chooses one tile, then calculates everything it needs, looks at all the geometry, does all the sampling, and reuses that data for each sample, rather than calculating it again and again for every single sample. So it can get quite slow if you turn that on. Now the next thing is the tile order and tile sizes. Now, I did quite an in-depth study on this a while ago, and that's the reason why I wrote this auto tile size add-on. Now, let's just go ahead and turn this all the way up to 256, and this is using CPU rendering still, and let's see how long it takes. Now I've turned that back off, so let's see. It was previously a 12-second render, and now that we've increased the tile size to 256, it is a 14-second render. So that's not that much. But now let's switch to GPU rendering and see how that works. So GPU rendering, let's do it around 256 and see how quick that is. That was pretty damn quick. 4 seconds, 4.39 seconds. And you can see that my subsurface scattering shader is now black because it's not currently supported. It hopefully will be in the next few versions, but we'll see. Okay, so let's go to a new slot. Change the tile size to around 32. Now this isn't completely accurate. Oh, let's turn it off and see what happens when you just make it exactly 32. So let's render it. And now you can see it's already past the 4-second mark. It's already double the render time and it's not even finished. So as you can see, tile size makes a huge difference for GPU rendering. Not so much for CPU, but it's rendering 4 times slower just because we're using a smaller tile size. So that's kind of strange. It was the other way around for CPU rendering. So anyway, keep that in mind, around 256 for GPU rendering and around 32 for CPU rendering. Now the reason there is a difference for GPU rendering is possibly for 2 things. One reason would be because it constantly has to, well not constantly, it has to change the tiles more often, so you know, every time it switches to a new tile it does a couple calculations, and that adds up over a while. The second reason is because your GPU literally has hundreds of cores. There aren't enough pixels for your cores. Maybe each core is rendering 1 pixel, so once you run out of pixels, most of your cores in your GPU aren't actually doing anything, so that is why it is slower. Now the next thing I want to show you, which is the last of the non-destructive methods, is with branched path tracing. So let's just render an image again, just to get a benchmark. Whoops, I need to change our tile size back down. Just to get a benchmark of how long it should take with our scene as it currently is. Okay, so 11 seconds, 11.73 seconds. Now, branched path tracing does look quite intimidating at first, but it's quite simple. Where path tracing, our main render samples are over here, and those are 20. Now, branch path tracing, your main render samples over here, the AA samples. And you want to keep those maybe around 16 or 32 or 64, depending on how clean you want it to be. And then you've got all these samples over here which allow you to maybe sample the transmission a bit more, which is what we want to do because there's a lot of noise over there. Maybe sample the subsurface scattering a bit more, maybe the volume a bit more, and maybe the glossy a little bit more as well. But the main reason this is useful is because the diffuse is kind of clean. We don't want to sample that any more than we need to, but everything else needs a little bit more clean as well. So let's go to another slot and render that. So that took quite a lot longer, 36 seconds instead of 11, but if you zoom in, it is quite a lot cleaner overall. So let's try and match up those render times. It's basically 3 times longer, and it's hopefully 3 times cleaner. But let's reduce our rendering samples by a third, so 5, let's see. And there we go, that's 12 seconds, that's pretty much the same as 11. So if you zoom in and switch between them, you'll see that it is a little bit better in places, but it's overall pretty much the same. Now, it is a little more noisier in the places that were a little bit cleaner, but in the places where it was noisy, it is a little bit cleaner, especially with subsurface scattering and the volumes. So basically, branch path tracing doesn't really save you any render time, it just lets you choose where you want the render time to go. And that is pretty cool. So, that is it for our non-destructive ones. Now for the destructive optimizations, we're going to be compromising a bit on the quality of our render. So I'm just going to go back to path tracing. And let's see, the first one I want to show you is no caustics. Now, I'm sure you already know about this one, but basically no caustics disables your caustics. And that is okay, it reduces a lot of noise, saves you a bit of render time, but honestly I think caustics are an important part of realistic rendering. So you can see that took about a second quicker, and we no longer have all that noise floating around on the other side. But now I want to keep this. I like this. It's bright. It's, accurate. This looks dark and fake. I mean, glass is transparent. This light is supposed to go through to the other side. So there's a couple things we can do to fix this. Now, to start off, let's just enable that how it was. One of the things we can do is this filter glossy over here. Now this basically, as the tooltip says, it kind of blurs the glossiness. It interpolates the samples. So if we set this on 1, and render that, and compare it to the render that also had caustics, you can see that it is a little bit darker, but it's not as bad as when we disabled caustics completely. And we've also gotten rid of most of the noise over here. Now, it is a little bit too much, I think. We could have a little bit more caustics over here, because it's kind of darkening it and blurring it too much. So rather than putting on 1, we can put it on something like 0.3, or even 0.2. Well, let's see what 0.3 is like. And that's pretty good. Gotten rid of most of those fireflies quite nicely. And that's pretty cool. Okay, so the next thing I want to show you, let's just disable that, is the clamp indirect. Now this one's pretty cool as well. It's very similar to filter glossy. It basically clamps the brightness of our samples. Of the indirect samples actually. And the reason that's cool is because fireflies are actually just really bright samples. There's nothing special about them. If you left it for long enough, those fireflies would average out with the pixels around them and it would look fine. But now if we clamp those samples, then we don't notice those fireflies as much because they're pretty much the same color as everything around them already. And you can see it does quite a good job. But it also darkens our highlights, or the highlights of our refractions and things like that. That is a little bit, it's a little bit weird, but it's a pretty good compromise for getting rid of all that noise. We could use it in conjunction with filter glossy as well, and that will be a pretty good teamwork. So, the next thing is a little bit more complicated. The main reason we're getting all this noise down here is because the light is hitting the sphere and bouncing off around it. Now, what we could do is pretty much just change the sphere into a white diffuse ball, and we would get rid of all that noise. Now, of course, we don't want to do that because we want to see a glossy ball. What we can do is make the rest of the scene see this glossy ball as if it were a diffuse ball, but we would still see it, the camera would still see it as a glossy one. So what I mean by that is, if I just go and select it and go to its nodes over here, is basically we tell the camera to see the glossy shader, but we tell the rest of the scene to think of that sphere as a diffuse shader. And how we do that is just with a light path node and a mix shader and the is camera ray. Just like that. Done. So the is camera ray, if it is a camera ray, it will look like a glossy, but if it's not a camera ray, it will look diffuse. So let's go and render that. Or maybe let's just turn off that clamp indirect so we can compare it with our original render. So there you go. It's no noise at all down here. Now this is kind of similar to disabling caustics, but not really, because if we say no caustics, then rather than being a diffuse shader that the rest of the scene will see, the rest of the scene will see a completely black shader. So it makes quite a difference. Anyway, that is pretty cool. Now we could do the same thing to all of these shaders and it will help quite a lot, but let's not really bother doing that. I'm sure you get the idea. Now that is basically it for general optimizations and that sort of thing for most scenes, but now let's do some things in particular, like multiple important sampling for mesh lights. So this scene is just a material ball thing with a single mesh lamp. Now by default multiple important sampling is on, but just to show you what it actually is for, I'm going to turn it off and render an image. Now it is noisy as hell, right? And if I turn it on, it is pretty good. So you think, it's always a good idea to have that on, and that's why it's on by default, because most of the time it is a good idea. But now if I go and unhide all of these other objects in my scene, which is a second light source and a ground plane, which is actually emitting light as well, and I render it, you can see that it is noisy as hell again. And the reason for this is because the ground plane, which is a light source, you can see it's emitting some light, is not actually an important light source, but multiple important sampling is turned on. So if we turn it off for the large object that is emitting not very much light, we're basically telling it that it's not an important object and it shouldn't be treated like a important light. So let's render that again, and you can see it's nice and clean again. So that is what you want to do with that multiple important sampling. Finally, another common mistake people make is using a whole bunch of detail in their procedural textures that they don't really need. So let me go ahead and render this guy. So that took 48 seconds basically, which is quite a long time for just a sphere. Now it is more samples than last time, it's 100 samples, so it's fairly clean, but that's still quite a long time for just a little sphere and such a tiny image. And the reason it's taking so long is because there are some procedural textures here. One for the bump mapping, which has a detail of 12, and one for the diffuse texture, which has a detail of 16. Now if we just reduce this so that it doesn't, so that we can hardly tell the difference, well, let's just go and see. Let's Control-Shift-Click this guy, and maybe go into local view so we can see properly. So with the detail of 16, it's quite nice and detailed. This is a Musgrave texture, but if we can go all the way down to something like 5, or maybe not 5, 6, it's pretty much the same amount of detail as when it was on 16. So, we don't need to go that high, and it's not such a visible texture anyway. Now our bump map over here has a detail of 12. If we turn it all the way down to 4, it doesn't look like it's changed at all, but it's so much less to calculate. So let's go and connect that back together, and go out of local view, not that it actually matters, and render that again and see how long it takes this time. So 39 seconds as opposed to 48. That's quite a big difference. That's almost 25% less. So that is pretty cool. The other thing we could do in this case is to tell the camera to see this material as it is, but tell all the other rays to see a simple green diffuse shader. So that is what we will do by adding a light path node, another diffuse node, and another mix shader. Whoa. Plug that guy into there, and the camera ray into there. So basically, the camera will see this material, but everything else will see this material. And if you're ever not sure about what's happening, you can always just connect an emission shader to the one that the camera is not supposed to see. Like that. And then you can see that it looks good to the camera, but it is also obviously emitting light. So that is the right way around to do it. Like so. And of course change this to a green color. And let's just use the same green color as that one over there. And that should shave off a few seconds as well. Yep, it is now 36 seconds instead of 39. Now sometimes that might not actually help, but sometimes it will make quite a big difference. Ken Trammell did a tutorial once on this, on CG Cookie, where he claimed that it made quite a significant difference. Anyway, that is it for this video, and that is it for the end of this DVD. I hope it helped a lot. I hope you're now a proficient Cycles user, and you know how to do your thing. So again, thanks for watching, and I'll see you next time.